and he'll talk about energy minimization problems.
Okay, thanks a lot, Stefan, for the introduction. So I really want to thank all the organizers for making this event possible, for inviting me. It's great to be here. One other thing that I realized shortly before this conference, this is a milestone for me. I think this is the first conference where I am the oldest one among all the speakers. I checked, and I think that's true. Yeah, thank you. Thanks. No, but I'm also really glad about this. This means this is a very fun conference, and yeah, I'm really glad to be here. It's nice. So, okay, so I'm giving this mini course on energy minimization problems in analysis and discrete geometry. So this was a big chunk of what I was working on in the recent years. Yeah, let me start right away by defining the main objects that I will be looking at, and because energy can obviously mean lots of different things. So here I will be talking about the so-called pairwise interaction energies. So in the discrete case, well, we'll always have some domain, and in most examples it will be the sphere, although in general it could be some other domain. And you have some kernel. So again, in most examples, at least today, this kernel will be continuous, so symmetric and continuous on the domain. Of course, a lot of interesting energies deal with singular kernels, but for today at least, I will not deal with them, but we'll see some tomorrow. Okay, so the discrete energy is just the sum of all these pairwise interactions. If you have a set of n points, you sum all of the interactions. I like to normalize them this way, but in general you don't have to. In case of singular kernels, of course, you have to exclude the diagonal terms because yeah, they will be infinity. And the energy integral or continuous energy is the double integral of this form, where you take an arbitrary probability measure on the domain and you compute this double integral. So the way to think about this intuitively is that in the first case, in this discrete case, you're putting n particles on the domain, and those particles interact according to the potential given by k, and you're trying to minimize this energy. So that means you're trying to find the equilibrium distribution of particles under this interaction. And you can think about it, and in the second lecture we'll see it, you can think about the Coulomb interaction, the electrostatic interaction, and even in this simple case, this problem is very interesting on the sphere, for example. And beyond the sphere, it's completely unclear. And in this case, you're thinking about it as if you're putting a continuous charge or a huge number of particles on your domain, and they're interacting, and you're looking at the equilibrium distribution. Yeah, of course, the two problems are related. If you understand everything about this problem, you will, of course, understand this problem by taking weak star limits. Vice versa, it's not quite the case. Of course, the discrete problem is more delicate. Okay, and then just the last thing, I use this normalization because in this case, these two definitions are very compatible. And I will sometimes abuse the notation going between from one to the other. Okay, so problems like this come up in many different areas. And actually, I remember vividly, I think this was like 2014, and I was at a conference at the Schrödinger Institute in Vienna, and there was Salvatore Tarquato. He's actually a physicist, but he goes to a lot of math conferences, and he made this cavalier statement in the beginning of his talk that every problem of discrete geometry is actually an energy optimization problem. So, and somehow this stuck with me. Anyway, so let me start with the very first object that I want to talk about, and this will be the central object for this lecture. And we will talk about lots of extensions, generalizations, versions of this particular inequality. By the way, this is going to be some sort of a mixture of a lecture, like a lecture for students, and collection of open problems and so on. So I cannot really give you a specific genre of this talk. Anyway, so assume we have n vectors on the unit sphere, either in the real or complex setting. It doesn't really matter. And we compute the following quantity. So this is exactly the energy just as defined in the previous case, where the kernel is the inner product squared. Okay, the absolute value of the inner product squared. Okay. So then it's pretty easy actually to prove an inequality that no matter how you choose those endpoints, this energy is bounded from below by 1 over d. Okay. I think this inequality goes back to Welch, whose name will appear again quite a few times today, but I cannot imagine that it was not known even before. So the proof is very simple. It's essentially just throwing away the off-diagonal terms and Cauchy-Schwarz. So yeah, let's go over it quickly. You square things out. I'm doing it in the real case. In the complex case, you just have to put the bars in the correct places. It works exactly the same way. Expand this square, interchange the sums. Now put things together, so these two sums in I and j are the same, this is a square. Then, okay, so these terms are non-negative. Throw away all the off-diagonal terms. Okay, leave only the diagonal terms. And then here we have, I want to put this sum inside the square, so to do that I use Cauchy-Schwarz. There are d terms, so I pay a price of 1 over d, right? So, and then I interchange the summation again, and we're on the sphere, so this inner sum is 1. Okay, that's it. That's the whole proof. Okay, and I'll actually give you in a couple slides. I'll give you an even simpler proof of this fact, but I think it would have been harder to come up with unless you already know the answer. Okay, so let's analyze really quickly when you get equality here. Okay, so what did we do? We threw away off diagonal terms, so you would get you need them to be 0, right? And you also applied Cauchy-Schwarz here, which means that all of these terms have to be the same for this to be equality. Okay, so yeah, let's sum it up. So you need these guys to be 0, and these are, and I'm sorry, I forgot a star here. Okay. So star stands for the transpose or the complex transpose, if in the complex case. Okay, and yeah, and you need to get a constant here. Okay, so if you put these two conditions together, that tells you that the sum of these outer products, the sum of these d by d matrices, gives you a multiple of the identity. Okay, it's actually really easy to check that that constant should be n over d. That's the so-called redundancy. How much more you have compared to the dimension. Okay. Well, now if you just take this relation and multiply it by x on both sides, you will get this equality. So this means that for all x you have this expansion, which looks very much like the orthonormal basis expansion, only you have a constant in front. Or also you can, if you multiply by x again, you would get this, so you get an analog of Parseval's identity only with a constant. Okay. So what does this tell you? So that tells you that in order to have an identity, you need these vectors to act like an overcomplete orthonormal basis. This has a name. These are called tight frames, or in particular, in this case, they're unit norms, so unit norm tight frames, often abbreviated to UNTF. You will see in this talk, people who work in frame theory, they really love abbreviations. You will see a few more later on. Okay, so basically this tells you that this inequality is achieved if and only if this configuration of vectors is a tight frame. Tight frames is an object that has been studied for a long time. It comes up in functional analysis, in signal processing, in quantum information theory, and so on. So basically, these are overcomplete bases as they perform well. So you have redundant information. So even if some information is corrupted, they perform really well. One way to, if you're wondering whether they exist, well, there's this super trivial way to construct a tight frame. Take two orthonormal bases and concatenate them. That will be a tight frame with redundancy 2. Okay. Also, for example, in dimension 2, you can take 3 equiangular vectors, the so-called Mercedes-Benz sign, right? So that's also a tight frame, or a simplex in general in d dimensions. Actually, people use that name. They're the Mercedes-Benz sign. Yeah. So these objects exist. I'm lying, cheating a little bit here because we don't really know that they exist for all n starting from d. Well, it is known actually. It's been known for a while, but actually it can be proved from these energy type considerations. I'll get to that in a moment. So they do exist for all n equal to d on the above. Okay. All right, so let me, as I said, I will state another proof. So here is an easier, if you speak linear algebra language, then this is a very easy proof. And actually, you will recognize that it's more or less the same idea. We're never using Cauchy-Schwarz here, but you're doing you have a quadratic polynomial essentially, so that's how you prove Cauchy-Schwarz, right? So you can rewrite this frame energy. So this is often referred, in the literature you will often see it referred to the frame potential. I like calling it frame energy because the potential is really the function that you're the kernel. Okay, so you can write it, if you write the matrix consisting of these vectors, you can write this frame energy as the Frobenius norm of this matrix, of the ZZ star. And, well, it's just the sum of the squares of the elements, right, of the matrix. And then, well, you can just write this. Well, this is exactly how you prove the Cauchy-Schwarz inequality, right? You write this quadratic expression, expand it, and now you just need to compute here. This is a d by d matrix. All the entries are n over d on the diagonal and 0 otherwise. So that's why you get this. And here in this matrix, you also get all ones on the diagonal, so you'll get the same thing here. Okay. So, and that's the whole proof. That's a much more concise way to prove the same inequality. Okay. And also, you can see that the only way that the inequality is achieved is if this is 0, if ZZ star is actually equal to constant times the identity, which gives you a tight frame. Okay. By the way, feel free to stop me if there are any questions. Okay, well, there was a nice paper by Benedetta and Ficus in the early 2000s where they proved an interesting fact that in this case, actually all the local minimizers have to be tight frames. And this implies, by what we already know, that then they're global minimizers. So tight frames are global minimizers. It means there are no local minimizers. And in particular, this implies that for all n, starting from d, tight frames exist. Okay. And the argument was technically a little bit involved, but essentially it's the Lagrange multiplier. So essentially, you could be an undergraduate student to do that, to understand that, and even to do that. And there was a fairly recent paper by Dustin Mixon and co-authors where they gave 3 alternative proofs of this fact. Actually, one thing I want to say is that this behavior is quite uncharacteristic. And in particular, if you're in the electrostatic situation, you have lots of local minima which are not global minima. So there is something special going on here that you don't have any local minima, that all the local minima are global. Okay. This inequality can also be easily extended to the continuous energy. Well, first of all, you could just run the same proof, replacing sums by integrals, or, well, you could just take the limit as, you could approximate any measure by discrete measures, equal weight discrete measures, and they take weak star sense and take the limit. Right, so you see that the right-hand side here is independent of n. So that's important. So you get this to the same bound. Okay, and then if you run that proof again, you can see which measures actually saturate this inequality, which measures are minimizers, and those are exactly so-called isotropic measures. So these are measures that satisfy this relation. In some sense, these are measures which act the same in all directions. Okay. And in particular, the situation here becomes quite interesting. You have a whole zoo of minimizers of very different natures, and later on, we will encounter many such situations. For example, well, we know tight frames are minimizers, right? So the sum of delta masses at tight frames. But also the uniform measure obviously has this property and it's a minimizer. Okay. And also another way that you can state this inequality, which we'll also see later, is that, well, if you, so sigma here stands for the normalized uniform measure. It's a measure, uniform measure in the sphere of total mass 1. Well, this 1 over d, it's actually a very simple computation that 1 over d is the value of this integral when mu is equal to sigma. So this says that the uniform measure minimizes this integral, which in plain words you can say that minimizing energy leads to uniform distribution. Okay. As we shall see, it's not always the case, but in this, here it is. Okay. And we shall actually today, by the end of the lecture, we'll figure out when it is the case. Okay, so let's actually now return to Welch's work, which I mentioned, that he actually proved that inequality as a tool to prove this bound, which is sort of important, very well known in coding theory. So this quantity is the so-called coherence. So you look at the vectors, different vectors in your collection, and you look at the inner products, and you want to understand, well, how far away the vectors can be, how spread out they can be. So you want to look at the maximal inner product that corresponds to the minimal distance between the vectors, and you want to make it as large, the distance as large as possible. So, so Welch proved this inequality, and this is known as the Welch bound. Okay. That this maximal inner product, absolute value of the inner product, is at least this big. Okay, and it follows in one line from the frame energy. So we have this inequality, right? Just proved it. And then if you look here, you have the diagonal terms. They give you 1, and there are n of them. Okay, and you have off-diagonal terms, and all of them give you at most gamma squared. Okay, and there are this many of them. Now you solve it for gamma, and you get this inequality. Okay, so it's very easy to prove from the energy estimate. Now let's try to understand when you get equality here. Okay, and two things have to happen. Here, you need to have a tight frame, right, as we just discussed. And here, in order to get equality, you need all the angles to be the same. Okay, so the absolute values of the inner products need to be the same. So if you look at the angles between the lines generated by these vectors, all of those angles have to be the same. So this naturally brings to the concept of equiangular lines. Okay, so, and the question is, how many equiangular lines can one have in d dimensions? Okay. And so far, everything we said was the same for real and complex case, but now we'll see that there will be a difference. Okay. So let's try to answer this question, how many equiangular lines one can have. It's actually a huge area, so I'll just scratch the surface a little bit, but I'll give you some interesting food for thought at least. Okay, so here's the first lemma, which is pretty simple. If you have an equiangular collection of vectors, then the outer products, zi star, have to be linearly independent. Okay, I'll do it in the real case, complex case. Well, no, it's actually the same in the real and complex case. Okay, so the proof is standard. Assume you have a linear combination that's equal to 0. Okay. Now act with zj star on the left and zj on the right. Okay, and then you'll just get the absolute value of the inner product squared, right? And this works for every j, so you have a system of equations where you have this matrix on the left, right? Because all the inner products for I not equal to j are the same. Okay, okay, and now it's trivial to show that this matrix is invertible. You can do whatever. There are at least 10 different ways to do it, and yeah, that implies that all lambdas have to be 0, right? So they're linearly independent. Okay. What that actually tells you, that they're linearly independent, well, it tells you how many of them there can be, right? So it tells you that in the complex case, it's at most d squared, right? So that's the dimension of all d by d matrices. In the real case, there is a difference. In the real case, all of these matrices are symmetric. Okay.
This is the tensor product.
This is the outer product. This is z times z transpose. Yeah. So it's a d by d matrix. Yeah, they're d-dimensional vectors, so you get a d by d matrix. And so these matrices are symmetric, and that's a subspace in the real case, and the dimension of this subspace is this. So here we'll already see a difference between the real and the complex case. Again, this I think this argument first appeared in the paper of Lemons and Seidel, and I think they attribute it to personal communication with Gerzon, and I think it's often called the Gerzon bound. Okay, so a couple more little observations in this case. So it turns out that if you actually achieve this value, okay, either in the complex or in the real case, you actually get that this equiangular set of equiangular lines is a tight frame. And the argument is almost the same as what I had on the previous page, because, well, If you achieve it, that means that they span the set of all matrices. In particular, you can write the identity as a linear combination of these matrices, but then you run essentially the same argument, and you will see that all the lambdas have to be the same. Okay? So that means that the sum of these guys is a multiple of the identity, so you get a tight frame. Okay. So if you have a maximal possible collection of equiangular lines, then you get a tight frame. Okay, here I just computed, just in case we will need it before, we'll need it after, what you get for gamma for the coherence if you achieve these bounds. Okay. All right. Well, so it turns out that in the real case, there are some additional restrictions. Okay. And in particular, so if n is large enough, greater than 2d, the twice the dimension, you have that, and if you have an equiangular collection, then 1 over gamma has to be an odd integer. Okay, so it's an interesting restriction. Let me show you. So this can be done pretty easily with linear algebra. So consider the Gram matrix. So these are d-dimensional vectors, so the rank of the Gram matrix is at most d. So the dimension of the kernel is greater than d because capital N is greater than 2d. Okay. So 0 is an eigenvalue with multiplicity at, greater than d. Okay. Consider this matrix now. Okay. So you will subtract the diagonal terms, the diagonal ones, and then you will divide by gamma, where in the real case all the entries off of the diagonal will be plus or minus 1. Okay. And then we know that negative 1 over gamma is an eigenvalue. Okay, because 0 was an eigenvalue here, 1 is an eigenvalue. Sorry, so this needs to be, yeah, it should be negative 1 over, I'm sorry, I need to take y minus g. Okay, sorry. Yeah. Okay, and the multiplicity is of this eigenvalue is greater than n over 2, right? So, so greater than d, which is n over 2. So so you get more. The multiplicity of this is more than a half of the degree, which means that it has to be rational. Because if it were not rational, then you would have conjugate eigenvalues, okay, with the same multiplicity, but it cannot happen. Okay. All right. So, but if it's rational, it's an algebraic rational, has to be an integer. Actually. So if it's a root of a monic polynomial with integer coefficients and it's rational, it has to be an integer. That's an easy exercise. So that proves, sorry. That proves that 1 over gamma is an integer. Okay. And if you want to take it further, you do a little bit more manipulations. You take the matrix of all ones minus the identity to kill all zeros here, minus the matrix that you constructed before, and then divide it by 2. So you will get plus or minus 1s off of the diagonal and run the same argument again. Okay. And you will get that it's actually an odd integer, not just an integer. Okay. So, okay. So given this lemma, one can easily show that if you have a maximal collection of equiangular lines with this maximal possible cardinality, then unless the dimension is 2 or 3, in which case this is possible. In dimension 2, of course, you take the Mercedes-Benz. In dimension 3, you take the icosahedron, and you take the opposite lines going through the opposite vertices of the icosahedron, and there are 6 of those. So that's 3 times 4 over 2, right? And otherwise, it has to be a square of the even integer minus 2. Okay, so it's very easy to prove it from what we just realized, because we know we computed on the previous slide that the coherence has to be 1 over square root of d plus 2, and then you just plug it in. Okay. It is true in dimensions 7 and 23. Okay, so 9 minus 2 25 minus 2. And those constructions actually have to do with the E8 and the Leech lattice, as you can guess. But it's known that it's actually not true in dimension 47. Okay, so you don't have the maximal number of angular regular lines is strictly less than that. So this is a complicated proof that's based on the proof is based on the proof of non-existence of certain strongly regular graphs. Okay, and almost nothing is known about this situation beyond that. And generally, for some small values of the dimension, there has been a lot of work with partial results about the maximal number of equiangular lines in the real case, but not really much is known in many cases. It's just the range. There is a lower bound and the upper bound, and there is not even a hope for a good general formula for all dimensions.
So,
yeah.
So you're saying that, so if you have a Kiesing configuration, that will give you some, what's the name you use? Equiangular lines, right?
Right.
Yeah. So this is where you were saying that the bound is coming from, this one, that you can actually achieve this because you just take the Kiesing configuration from the Leech lattice. And
Right, yeah, essentially. Yeah. Mm-hmm.
Is there any upper bound or lower bound that you can get coming from Kiesing members? Like some trivial ones?
Good question, not that I know of the top of my head. Okay. All right, so let's now switch to the same problem, but in the complex case. There more is known, and also it's clear what it should be. It seems clear, at least, what it should be. So in that case, the upper bound was d squared, and it appears that d squared is almost achievable. Okay, so this is the famous Zauner conjecture. I stated in a weaker form. So the Zauner conjecture even states that these objects should exist of a certain form, as an orbit of Weil-Heisenberg group. But and actually, there's this name I told you about abbreviation. The SIG-POVM stands for Symmetric Informationally Complete Positive Operator Valued Measures. But let's not worry about that. So so let's just ask this question geometrically. Is it true that in any dimension d, in CD, there always exist d squared equiangular lines? So just that. And it seems that the answer is yes. It's conjecture that it's yes. It is proved up to dimension 53, and for a few other values of d, there are some known constructions. There are numerical constructions for even more values of d where it seems to be where it seems to work. There are certain conjectures about what it should look like, but in general, the conjecture is open. Okay, this is a big open problem. One thing that I wanted to mention in relation with this open problem, well, actually, by the end of the lecture, we'll know how to prove it, but if this object exists in CD, then it minimizes this energy with power 4. We already know that it minimizes the energy with power 2 because, well, it has to be a tight frame. But it's a computation that shows that it also minimizes this with power 4. So in the next lecture, we'll actually talk a little bit more about spherical designs. So this sort of tells you that it's actually projective design. Actually, most of the problems that I talked so far, the correct setting for them would be in the projective space instead of the sphere, because here nothing changes if I take one vector and change it to the opposite. Right? But geometrically, it's much more clear if we discuss things on the sphere. Okay. I will return to this. I will actually tell you a little bit later one of the ways to prove this. But what I want to mention now is that this has actually been used in the search for such configurations. So you consider this energy, you try to minimize it numerically with certain restrictions, and some configurations have been obtained this way. Okay. All right, let's now move on. And since we just talked about power 4 in this energy, let's ask a question. What would happen to this frame energy if I change the power here? Okay. And this is also known as the Welch bound. So if you change the power 2 to other integer powers, there is this inequality. And let me give you one possible way to prove it. Okay. Although there are others, but this is the most classical. It's a very powerful and very useful trick. Has its own wiki tricks page, so-called tensor power trick. So basically what you do is the following. Let's consider k-fold tensor power of CD. Okay. So this is the standard basis then. Okay, and then if we take tensor products of vectors, okay, then the inner product with respect to this basis, this will be just the product of the inner products. Right? That's the standard computation. In particular, if you take the vectors zi and tensor product them with themselves, you will get power k here. Okay, so in that sense, you can look at the left-hand side. That's precisely the frame energy, but for the configuration of this tensor products, right? The tensor powers. Okay. So you replace your vectors with their tensor powers, and then you apply the frame inequality. And if you do it stupidly, you would just get 1 over d to the k here, because that's that's the dimension of the space of the tensor product. But if you do it in a smart way and you realize that here all these tensor products are symmetric. Nothing changes if you interchange the vectors here in the basis. So you need to compute the dimension of the symmetric tensor product space, and that's exactly this number. So this is the argument in a nutshell. So it's a very nice trick which allows you to always pull yourself out by the hair, right? So you're not doing anything new. You're just using the inequalities that you already had. Okay, but you constructed new objects for which to apply them. And it's actually known that this inequality is sharp. It's sharp in the complex case. You can construct. So basically, what do you need for it to be sharp? You need these tensor powers to be a frame in the symmetric tensor product space. Okay. And that's possible. So this was done by Data and collaborators. But it turns out that this inequality is not sharp in RD. Okay. So in RD, you can prove a different lower bound. Okay. And if you compare the two, this lower bound will be strictly greater than this one, as long as k is greater than 1. So when k is 1, you get the frame bound, and it's the same in real and the complex case. As long as k is greater than 1, you get two different bounds. Okay, and where does this bound come from? So this bound, well, actually this is the value of this integral, of this integral energy. And so then what this inequality essentially tells you is that this energy with this kernel, it's minimized by the uniform measure. Okay? And so now comes the time to answer the question, when are energies minimized by the uniform measure? Okay. And actually, I'll start the introduction to this question trying to avoid as much as possible, for as long as possible, using spherical harmonics or Gegenbauer polynomials. So I'll start it with a completely elementary approach. Okay. Most places would actually start this immediately, would introduce spherical harmonics and Gegenbauer polynomials right away. Okay, so let's talk about positive definiteness. That is the property that is very turns out to be very important in this setting. So a kernel function of two variables is called positive definite if whenever you choose n points and write this analog of the Gram matrix, then that's a positive semi-definite matrix. Okay. This is equivalent, well, okay, this is I just wrote down the definition, rewrote it. But now you can also approximate in arbitrary measures by discrete measures. You can rewrite it in terms of measures. I always like more analytic approaches here. So you can take any signed measure, okay, and the energy of that signed measure should be non-negative. Okay. Basically, because this expression that you get here, you can just write it as the energy of this discrete measure, okay, and then just take the limit. We'll also say that the kernel is conditionally positive definite if this inequality holds for all measures with mean 0. Okay. All right. Okay. So, any questions, by the way? No? So is everything clear? Okay, let's have a few simple examples of positive definite kernels. Assume we are on the on Rn, on Rd. The inner product is, of course, a positive definite kernel, okay, because because the Gram matrix is positive definite. Right? Any power, integer power of the inner product is also positive definite, okay, because by Schur's lemma tells you that if you take the Adamar, so element-wise product of positive definite matrices, that's still positive definite, okay. So also, obviously, you can take positive linear combinations, okay, and that will still be positive definite. Okay, I don't worry about convergence for now. Let's shove that under the rug. Okay, and actually, if you are on the sphere, okay, and if you have a kernel that's rotationally invariant, so depends just on the inner product, and it is positive definite on the sphere, on spheres of all dimensions, then this is actually equivalent. Then it has to be analytic and it has to have Taylor series with non-negative coefficients. So this is the result of Schoenberg from the same paper that we will discuss tomorrow. So this is the second part, which is often overlooked. So the first part is about Gegenbauer polynomials, but if it happens in all dimensions, then you actually have this relation. So one direction we already know that this is positive definite, but these are all positive definite kernels in this case. Right, so now this tells you that, at least in the real case, the kernels that we looked at so far, they were all positive definite. Okay, so and probably that has something to do with integrals being minimized by the uniform measure. So, and indeed, that is true. So there is a thing that I like to call magic identity, which is super simple. It's a computation. It's a middle school computation, essentially. So you have this relation. So somewhere in the sphere, the kernel is rotationally invariant. You have any measure with total mass 1. Doesn't even have to be a probability measure, could be signed. Then you have this relation. What does this relation tell you? So the energy is a quadratic functional of the measure, right? But it tells that near sigma, it behaves linearly. Okay, and the proof is very simple. You expand this quadratic functional, right? So you have this, and then you have the cross term. And in the cross term, let's integrate in sigma first, okay? And things are rotationally invariant. The answer does not depend on x, right? So this integral inside does not depend on x, it's constant. But also that tells you if it does not depend on x, it should be the same as the double integral, because if you integrate in sigma again, you'll get the same thing, right? So, and then you get, so you just get this difference. That's it. Okay. Okay, so that's clear. So again, this is a middle school computation. Now this immediately tells you that if your kernel is positive definite, then sigma minimizes the energy, okay? Because if the kernel is positive definite, this quantity has to be non-negative, right? And so then this means ik of mu minus ik of sigma is greater than or equal to 0, okay? And so it's not just minimizing energy among all probability measures, it's among all signed measures of total mass 1. Also, you can easily deduce the converse. It's not so easy to deduce it in the case of just probability measures, but if you know that sigma minimizes the energy among all signed measures of mass 1, then the kernel has to be conditionally positive definite, because then this quantity would always be non-negative for any mu minus sigma, where mu is a signed measure of mass 1, so any measure of mass 0 could be written this way. Okay. All right. So this gives you the answer without saying a word about Gegenbauer polynomials. And in particular, it applies, with some tweaking, it also applies to the complex case and the kernels that we were considering so far, powers of the absolute value of the product. Okay. would it apply to other geometric situations? So what would you really need in this case? What you would need is, let's see, you would need this property, this main property, that when you integrate the kernel with respect to that hypothetical minimize and measure once, you get a constant on the whole domain. Okay. This quantity, this property is not too unexpected, because in potential theory, that's what happens when you have minimizing measures. Usually you, if you integrate once, the potential that it creates, at least on the support of the measure, has to be constant. Okay, and then, well, if you additionally assume that the measure has full support, then this becomes essentially an if and only if condition. It turns out that, okay, so these are the conditions when this magic identity holds, and with the help of magic identity and many other and several other considerations, it turns out that many different things happen to be equivalent. In particular, let me mention one. For example, you can prove a sort of local to global principle in this case. It becomes super simple. So if local minimizers in this case have to be global minimizers, if the magic identity holds, and you prove it in the following way. And local in this case, I mean sort of in a really weak way, so it's local in every direction. Okay, so assume you have, for a given measure mu, you have this inequality for some small value of t, and small may depend on mu, it doesn't matter. Okay, use the magic identity here to put sigma inside. Okay, so you get this, pull out t, you get t squared here, and you're left with this. Use the magic identity again. Okay. So you get, no matter what t is, it doesn't matter, you get that this quantity has to be non-negative. So if this measure sigma is a local minimizer, then it has to be a global minimizer. Okay. And yeah, at some point we figured out that there are lots of conditions that end up being equivalent. So I'm not expecting you to read everything that's said here. I just want to mention a few of the things. So first of all, there is equivalence between positive definiteness up to a constant and conditional positive definiteness, which is not true in general. Okay, let me first focus what we assume here. So we assume that the measure, so this special measure, so here mu plays the role of sigma in the previous slide. Sorry, this is copied from the paper. So mu has full support and is invariant with respect to the kernel k, meaning that this potential, if you integrate once, you get a constant on the whole domain. Okay, so under these conditions, you have the equivalence of all these properties. So first of all, conditional positive definiteness and positive definiteness up to a constant, which are not equivalent in general. You have equivalence between this conditional positive definiteness and mu minimizing the energy either locally or globally among probability measures or among all side measures of mass 1. This is also equivalent to the convexity of the energy functional, either locally or globally, and a few other things. Okay. In particular, this thing we'll talk about this more tomorrow. So here is another, a diagram which shows, of course, many implications here are true without any additional assumptions. Most of the implications are true if you just assume that the measure is invariant. Okay, and there are only a couple that require the measure to have full support. Okay, and it was actually funny when we figured out that all these things become equivalent. It's actually, I think there is value in writing up your thesis really well if you're a graduate student. So when my graduate student, then graduate student Ryan Matsky was finishing up his thesis, is when we started to realize that something is going on here. He started writing up all the background. We don't claim, oops, sorry about that. We don't claim that any of the implication is new in here. We haven't found some of them in the literature, but I wouldn't be so bold as to say that they're new. But it seems that it has never been realized that all of these things are really equivalent. All right, and I have 3 minutes, right? Okay, so I will just give a small appendix. so this term invariant measure, I will tell you about one problem, which is also sort of related to energy minimization and discrete geometry, where this term and this object also comes up. So, and this is the problem of so-called rendezvous numbers. Okay. So assume you have a convex domain. Compact domain, compact metric space. Could be pretty general. Actually, metric here is not important. You need a symmetric, continuous symmetric kernel. That's all you need, really. And then, so the following is true. For any set of points in your domain, it has to be connected. Yes. For any set of points, there exists a okay, so, sorry, let me put the quantifiers correctly. There exists a number, okay, corresponding to this metric space, so that for any set of points in the domain, you can find another point in the domain so that the average distance would be precisely that number. Moreover, that number is unique. Okay, so the domain uniquely identifies that number. Okay. I don't have time, but if anybody's interested, I can later show you the proof. It's a pretty simple min-max argument. Okay. Why is it called a rendezvous number? Because this, if you interpret those as people, so for any people living in this country, you can find a point for them to meet, so, so that the average distance traveled would be precisely that number. Okay. And you can again take the limits of this and reformulate it using measures. It would say that for any measure, there exists a point so that when you take the potential, so you integrate once and take the potential at that point, it would be precisely that number. Okay. Okay. And in this case, if an invariant measure exists, then it's very easy to find that number, because if the invariant measure exists, you just use it for that measure, use the definition for that measure, you get a constant. So it doesn't matter which point you pick, you would know exactly what the number is. Unfortunately, this number is known for very, very few shapes. Okay, so this, so pretty much pick almost any shape you want, and this would be an open problem. Okay. There are several survey papers about this subject, so I can share those links. And I will stop here. Thank you very much.
Thank you very much. Questions?